In today's lecture, we are going to discuss the intensity of sound waves. Actually, any wave possesses energy, and when a wave travels in a medium from one region of a space to another, then energy is transported from one part of the space to its another part. And this transport of energy is directly related to the intensity of the wave. So we can define intensity of any wave, but here the expression for intensity, particularly for sound wave, we will obtain. But when you define the intensity, that definition will be common, that will be valid for any wave. So now let us first of all see how we can define the intensity of a wave, or particularly sound wave. In fact, this intensity of sound wave is defined as the average energy crossing a unit cross-sectional area perpendicular to the direction of propagation of the wave in unit time. So you can see I have shown in this figure there is a surface here which I have marked by this this rectangle. This rectangle represents actually a surface. And let us consider that this surface is lying in YZ plane. Let us consider this surface is lying in YZ plane. And a wave is propagating in X direction. Then you can see this surface is definitely kept perpendicular to the direction of propagation of the wave. Now, as wave is incident on the surface or passes through this surface, it means the wave carries energy and it passes through this surface. In this condition, if you find the average amount of energy that will flow through unit area of cross section of this surface in a unit time, that is called intensity. Okay. So if you consider that the average amount of energy passing through this surface is equal to E, okay, and S is the area of cross section of this surface through which this average amount of energy is passing, and the time interval in which this much amount of energy will pass through this surface area S, that is T. So you can see in T time the amount of energy passing through surface area S is equal to this E. E is actually the average value of energy, because you will see when I will calculate the amount of energy flowing through this surface, that will be time dependent. So here average value has been taken. It means in T time through area S, average amount of energy flowing is E. So in unit time through unit cross sectional area, the amount of energy that will flow will be given by E divided by S times T. And in accordance with the definition of intensity, this amount of average energy passing through unit cross sectional area in unit time when the surface is kept perpendicular to the direction of flow of energy, that is called intensity. So intensity of this wave will be I equal to average value of E divided by S times T. Okay, S times T. So in this way you can define the intensity of any wave, and if you are talking particularly for sound wave, then this E will represent the average value of energy of the sound wave. Okay, so I have defined the intensity of this wave in this manner. But energy flowing per second or average energy transmitted through a surface in unit time, that is actually called the average power. So this E upon T will be equal to this P, which represents, I have written this P inside the angular bracket, and this angular bracket has been written for the average value. So you can say that the average value of E divided by time interval T, this represents the average energy flowing per second or rate of flow of energy. But this rate of flow of energy is actually the average power. So the average power transmitted through the through the surface, you can say surface, this is actually equal to E divided by T. So when you will write this average P instead of E over T, then intensity may be defined as average value of P divided by S. So what does it mean? It means through area S, the average power transmitted is P, and therefore through unit cross-sectional area, the average power transmitted will be equal to P divided by S. So in this way, this intensity can alternatively be defined as the average power transmitted across a unit cross-sectional area perpendicular to the direction of propagation. Okay. So you can define intensity of a wave in a simple manner, that it is the average power transmitted through unit cross-sectional area when the surface is kept perpendicular to the direction of propagation of the wave. This fact that surface must be kept perpendicular to the propagation of wave, this is very important, so you must state it. Okay. So this is actually the basic definition of intensity of any wave. But as our aim in this lecture is to find the expression for intensity of a sound wave, so now we will talk only about the sound wave, calculation of intensity, or to getting the expression for intensity of a sound wave. Okay. Now sound wave, you have already studied that this is a compressional wave, particularly in fluid when sound travel. Then actually sound wave has two representation. You have already studied it in my earlier video. This sound wave may be described in terms of the displacement suffered by the particles of the medium in the direction of propagation, that is as a longitudinal displacement wave. But when this sound wave travels through a medium, you have also learned that the pressure of the medium does not remain at its normal value, but it changes. During compression, the pressure of the medium increases, and during rarefaction, it decreases. So this excess pressure, this change in pressure, may be taken as a wave function to describe the sound wave. This is called its pressure representation. So sound wave, you have studied, may have two representation. First one is called displacement representation, and another is called pressure representation. And you have also seen earlier that these two waves, that is displacement wave and pressure wave, differ in phase by pi by 2. So if we will write the equation of displacement wave in terms of sine function, at the same time the same wave, when will be represented in terms of excess pressure, the equation must be in cosine function, so that they differ in phase by pi by 2. So now let us consider there is a sound wave which is traveling in x direction, and as just I have explained, this wave may be treated like a displacement wave or a pressure wave. So if you will if you will treat this wave as a displacement wave, then the equation for the displacement of the particles sub of the medium will be written as psi equal to a sine omega t minus kx. Okay, here you know this a is what? This is the displacement amplitude. Okay, omega is frequency of the wave or angular frequency of the wave, and k is the wave vector, or you can say the wave number. But when we will write the equation for the excess pressure developed by the wave in this medium, then that is written as P equal to P naught cosine of omega t minus kx. You can see the equation for psi is in terms of sine function and equation for P is in terms of cos function. So that you can say that the phase of the displacement wave differs from the pressure wave by pi by 2. Okay. Actually, this P naught, you know, this is called pressure amplitude. This is the maximum value of excess pressure. And you have learned earlier how the displacement amplitude A and the pressure amplitude P naught are related to one another. You have learned. So I have written here that this pressure amplitude P naught is given by A times B times K. You have already learned the proof of this relation earlier. But you know, this wave vector K, this is equal to omega over V, where V is the wave velocity or phase velocity. So this relation may be written as P naught equal to AB times omega over V. This is the relation between the pressure amplitude P naught and the displacement amplitude A. Okay. Now our aim is to find the intensity of this wave. So in accordance with definition of intensity, we will have to find the average power passing through any cross section, average power. And for this, let us consider there is a medium which I have shown here, and we consider a cross section at any point, let us say N. At any point N, we consider a cross section of this medium. And we also consider that this cross section is lying in YZ plane and the wave is propagating in X direction. Okay. So if you will consider a cross section, let us say of area S lying in YZ plane and wave is propagating in X direction, then you can say that this wave is traveling perpendicular to the direction of perpendicular to this cross section area, this surface or this cross section. Okay. Now, in fact, during this wave propagation, the medium which is in left side of this cross section, this is the left side. Okay. So the medium in left side of this cross section, okay, exerts a force which will be equal to what? That will be equal to P times S. P is the excess pressure and S is the area of cross section. So this is the resultant force that will be exerted on this surface or this cross section by the medium in left side of this cross section, okay, to the medium in right side. Okay. So you can say the medium to the left to it exerts a force equal to P times S on the medium to the right along the x-axis. Okay. Now, due to the application of this force PS, actually the particles of the medium suffers displacement, and so the points of application of this force move longitudinally, that is along the direction of force, with a speed what? What will be the speed with which this particle will move? You know, this psi represents the displacement of the particle at any time t and position x. So when actually you will differentiate this psi, which is displacement, with respect to t, you will get the velocity of the particle. Okay. Now, using the definition of power, how power is defined. You know, power is actually the work done per second or energy flowing per second. Okay. Utilizing this definition of power, now we will be able to find the expression for power, instantaneous power, and then we will find the average power. So let us see. I have calculated it here that this u is the velocity of the particles of the medium, which will be del psi by del t. Can you say why I have not taken here the ordinary derivative d psi by dt? Why this partial derivative? You can easily understand. You can see, since psi is equal to a sine omega t minus kx, so actually this psi is a function of two independent variables. One is x and another is t. So if you want to find the derivative of psi with respect to t, you must have to keep x constant. And that's why we must take the partial derivative of psi with respect to t, not the ordinary derivative, because it is a function of two independent variables. It depends not only on t but also on x. That's why this velocity is defined by del psi by del t. Okay. Now, as I have told you that power is what? Power P is defined as work done per second. Work done per second. So, and this, if you consider that this is dw work is done in time dt, then P is dw by dt. This is instantaneous power. And dw will be equal to f dot dr. F dot dr. This is the elementary work, and divided by dt. But you know, dr by dt, this is velocity. So power is simply defined as f dot u. That is a scalar product of force and velocity. This is actually equal to the instantaneous power. When you say instantaneous power, that means power at any moment t. But here you can see the force exerted by the medium in left side of this section acts in the same direction as the direction of the movement of the particle. So actually these two vectors f and u in present case is in same direction, and therefore angle between these two is 0. You can say that actually in this situation f is parallel to u, and therefore angle between these two vectors is 0. So in accordance with the definition of a scalar product of two vectors, you can write P equal to fu cos 0. But cos 0 is 1, so this is simply f times u. But you know, f is equal to P times s, and u is equal to del psi by del t. Okay. Now, actually we will substitute the value of this P and del psi by del t on the basis of this equation number 3. Psi is already defined here. This is a sine omega t minus kx, and and P is defined like this. So value of P will be directly written as P naught cosine of omega t minus kx, and del psi by del t. For this you have to differentiate this psi partially with respect to t, and that will be omega a cos omega t minus kx. So you can see I have substituted the value of P and del psi by del t using the equation number 3. So this capital P, which represents the instantaneous power at any moment t, that will be given as P naught times s times cosine of omega t minus kx times del psi by del t. This is omega a times cosine of omega t minus kx. So this instantaneous power P is simply equal to P naught S omega A cos square omega t minus kx. Okay, cos square omega t minus kx. This is the value of instantaneous power, that is power at any moment t. Okay. Now, in this expression, the first quantity is P naught, and you know P naught is actually the pressure amplitude, and you have just seen that this pressure amplitude is given by this expression. It is related to the displacement amplitude A by this relation, that is B omega A divided by B. And what is this B here? B, you know, this is bulk modulus of elasticity. This is bulk modulus of elasticity. We have learned already earlier. So the instantaneous power P is given as S omega square A square B over B times cos square omega t minus kx. So you can see that this power actually depends on the position x and time t. Okay. But according to the definition of intensity, we will have to find the average power passing through this cross section in a direction perpendicular to the plane of the surface. And for this, since quantity cos square omega t minus kx is varying if x is fixed, then this will vary with time, because surface is kept at a particular position, so x will be fixed. And you know, the average value, when we will take the average value of this cos square omega t minus kx for a given value of x in this equation 4, then we will get actually the average value of power. And what is the average value of cos square omega t minus kx? You know, the average value of this cos square theta for a complete cycle, that is between theta equal to 0 and theta equal to 2 pi. Okay, or you can say for a complete cycle or over a long time, that is simply equal to 1 over 2. Average value of cos square omega t minus kx for a complete cycle or over a long time, that is equal to 1 over 2. You can understand it. Actually, when you will find the average value of cos square theta or cos square omega t minus kx, this will be actually equal to 1 by 2 for a long time, or at least a time equal to its time period. Why? Because you know the minimum value of cos square theta is 0 and its maximum value is 1. So its average value will be minimum value plus maximum value divided by 2, and that is equal to 1 over 2. This is a simple technique to find the average of this cos square omega t minus kx. It is also found by the process of integration, but for remembering this fact, you can understand it in this manner, that when we will add the minimum value of this cos square omega t minus kx and its maximum value and divide by 2, we will get the average value. And its minimum value is 0 and maximum value is 1. So 0 plus 1 divided by 2, that will be equal to 1 by 2. So in this way, we get the average value of this cos square omega t minus kx. Now, when you will substitute the average value of this cos square omega t minus kx in this equation number 4, then you will get actually the average power transmitted through that surface. Okay. So now the average power which will be transmitted through the surface given by this P inside this angular bracket. This angular bracket, I have told you, this represents the average value of P. And that will be equal to average value of cos square omega t minus kx, this is 1 by 2, times this much. This is S omega square A square B over B. Okay. So how easily we have calculated the average power transmitted through the surface. Now remember, you have to find the intensity of this wave, and for this you must remember its definition. How intensity you have defined earlier? Actually, you have seen that intensity is nothing. This is simply the average power crossing through unit cross-sectional area. So when you will divide the average power P by the area of cross-section S, you will get the average value of power passing through the unit cross-section, which is called intensity. So intensity is given as average value of P divided by S. And when you will use this expression for average power and divide it by S, the S present here in the expression for P will cancel out, and your result will be omega square A square B divided by 2B. Okay, this is the expression for intensity, okay, in terms of the bulk modulus of elasticity of the medium, and in terms of A, which is displacement amplitude. Now actually this expression for intensity which we have obtained in this equation 6 can be expressed in different forms in terms of different parameters. Now you have seen earlier that the wave velocity of a compressional wave in a fluid is given by a square root of B over rho, where B is the bulk modulus of elasticity and rho is the density of the medium. What is the rho? Rho is density. And that's why you can write V square will be B over rho, and so B is rho times V square. So if your aim is to eliminate this modulus of elasticity B from this equation 6, you can write at the place of B rho times V square. So writing or eliminating B by rho V square, the expression for intensity of this wave will become what? This will be omega square A square rho V square divided by 2B. Now this V, one of the V in numerator will cancel out, and therefore I is equal to this much. This is omega square A square rho V divided by 2. Okay. And you may write this expression in this manner. This is omega square rho V divided by 2 times A square. Now you can see for a particular wave and traveling in a particular medium, the bracketed quantity will be constant. When you talk about a particular wave, its frequency is constant. And if you consider a particular medium, the velocity of a wave in a particular medium is also constant at a given temperature. And density for a particular medium is also constant. So this bracketed factor will be a constant for a given wave and for a given medium. And that's why you can say that the intensity of this wave is directly proportional to the square of its displacement amplitude. That is, I is proportional to A square. Actually, this result we have obtained particularly for a compressional wave like a sound wave traveling in a fluid. But when you say that intensity is directly proportional to a square of the amplitude of the wave, this is a general result. It holds not only for compressional wave, but this result is valid for any type of wave. Although here in present situation, the displacement amplitude A is a real quantity. But in general, when you talk about the different type of waves, this amplitude A may be complex. For example, if you are talking about the matter wave, in general A is complex. If you are talking about the electromagnetic wave traveling particularly in conducting medium, then A may be a complex quantity. So in general, for any type of wave, it is written that I is proportional to a square of the modulus of the amplitude. This modulus will be significant when amplitude is not real but complex. But in case of real amplitude, there is no need to write a square of modulus. We can say simply that intensity is proportional to what? Intensity is proportional to a square of the amplitude. Okay. But you know, sound wave has two representation: displacement representation and pressure representation. Here, the expression for intensity obtained, you can see, shows that this intensity is proportional to the square of the displacement amplitude. But you can show that this intensity is also proportional to the square of the pressure amplitude. And for that, you have to replace this A in terms of the pressure amplitude P naught. And for that, what you will do? You will simply use the relation which relates actually P naught, that is the pressure amplitude, and A, which is displacement amplitude. And you have just seen that the pressure amplitude P naught is related to the displacement amplitude A by this relation. P naught equal to B omega A over B. And that's why A will be equal to P naught B divided by B omega. Okay. But B again is written as rho times V square. You can see here. Okay. So when you will replace this B by rho V square, you can see this V and this V will cancel out, and therefore A will be given by P naught over rho V times omega. Now let us substitute this value of A in this expression for getting the intensity in terms of the pressure amplitude. So I will be now given by rho omega square rho V divided by 2. This factor is attached, and instead of A square, we will write this much. A square of this. This is P naught square over rho square V square omega square. And now you can see this omega square will cancel out. Okay. One of the V will cancel out. One of the rho will cancel out. Okay. And therefore I is simply equal to P naught square over 2 rho V. This is actually the simplest formula for measuring the intensity of sound. In your examination, sometimes question is asked to you: define intensity of a sound wave and prove that it is this intensity I is given as P naught square over 2 rho V. This expression will be already written in the question, and you have to derive this result. Okay. So for solving the numerical problem, you should remember this: I equal to P naught square over 2 rho V. And again you can see, in a particular medium, the wave travels with a particular speed V, and the density of the medium rho is also constant. Therefore, this factor 2 rho V will be a constant factor in a particular medium. And that's why you can say that intensity I is proportional to P naught square. So you can compare these two results. If you are talking about the sound wave in terms of displacement wave, even then you see that intensity is proportional to the square of the displacement amplitude. But when you talk about the sound wave in terms of its pressure representation, again you see that intensity of this sound wave is proportional to a square of its pressure amplitude. So this is a general fact, not only for sound wave, but for any wave. As I have told you, that intensity of any wave is directly proportional to the square of its amplitude. And in most of the cases, we simply take the proportionality constant equal to 1 for simplicity. Although here you can see the proportionality constant is not 1. In this equation A2, it is 1 over rho 2 rho V. In equation A1, it is omega square rho b divided by 2. But for calculation, for simplicity, in most of the cases we take this proportionality constant equal to 1, and people simply say that I is equal to a square of the modulus of amplitude. It is, you can use the result like this. Okay. So in this way we have obtained the expression for the intensity of the sound wave and obtained a very remarkable fact that this intensity is proportional to a square of the amplitude of the wave. Okay. Now in fact, when you talk about the intensity, this intensity is directly related to a particular property of the sound wave which is called loudness. In fact, this loudness of sound that we feel is mainly related to the intensity of the sound. Although this loudness is not directly proportional to intensity, but it is directly related to intensity of the sound. Or in fact, this loudness also depends on the frequency to some extent, but mainly intensity is the parameter that determines the loudness of a sound. Okay. You have seen that intensity I is defined as average power transmitted through unit cross-sectional area. And you know the SI unit of power is watt and that of area is meter square. So in SI unit, we measure the intensity in terms of watt per meter square. Okay. Now if you will talk about the response of sound intensity by the human ear, then it is found that our human ear responds the sound intensity over a wide range. Human ear can give response to the sound wave when intensity of the sound wave is at least 10 to the power minus 12 watt per meter square. What does it mean? It means the threshold intensity for human ear is 10 to the power minus 12 watt per meter square. It means if the source of sound wave produces sound, such sound whose intensity is at least 10 to the power minus 12 watt per meter square, then your ear can give response to it. Okay. It will feel that sound is falling on it. But if, for example, let us consider that the intensity of the sound wave which is falling on a human ear is 10 to the power minus 15 watt per meter square. Does our ear give response to this sound? Answer will be no. When intensity will be less than 10 to the power minus 12 watt per meter square, our ear cannot detect that sound. That the ear will be unable to detect such a sound. So for detection of sound or for giving response to the sound, the intensity of sound wave must be at least 10 to the power minus 12 watt per meter square. Okay. But now if you say that the intensity of the sound wave falling on the sound is 10 to the power minus 10 watt per meter square, this sound wave will be detected by the human ear or not? Answer will be yes, because its intensity is greater than the threshold intensity, so our ear give response to it. It feels its loudness. So in this way, as the intensity increases, human ear give response. But when intensity becomes 1 watt per meter square, then also our ear give response. but this is called painful response. But if the intensity is greater than 1 watt per meter square, then again our ear will be unable to detect it. That will be very painful and that will damage the human ear. So actually, in normal condition, a human ear responds the sound wave when its intensity lies between 10 to the power minus 12 watt per meter square to 1 watt per meter square. So you can say that this 1 watt per meter square is the upper limit of intensity that will be responded by the human ear. And this 10 to the power minus 12 watt per meter square is the minimum intensity which is responded by our ear. Okay. So you can see there is a large range of intensity that will be detected by the human ear. Okay. But this is not a very practical value. The common people does not understand the numerical value like 10 to the power minus 10, 10 to the power minus 9. It is a very small number. So for using this idea in practical sense, a logarithmic scale is used. If you have studied physical chemistry, then you have seen a concept of pH scale for knowing the acidic nature or the basic nature of a solution. What is that pH scale? Actually, pH scale is nothing. This is simply the measure of the concentration of hydrogen ion in a solution on logarithmic scale. So when in our calculation number is very small, in general we express such values on logarithmic scale so that a practical number comes. And this is the reason that actually we do not specify the intensity in watt per meter square, but instead of it, intensity is measured on a logarithmic scale. And when you measure the intensity on a logarithmic scale, that is called actually sound level. Okay. So what is this sound level? Sound level is nothing. This is the measurement of intensity on logarithmic scale. And how this sound level is defined? Sound level is, or you can say that loudness is measured in terms of sound level. And how this sound level is defined? This is defined as SL. SL stands for sound level. This is defined as 10 times log I over I naught. Here the base of log is 10. Okay. Log I, you can write here 10. This is I over I naught to the base 10. Okay. This is the definition of sound level to measure the loudness of a sound. Actually, here this I naught represents the reference intensity. When you say reference intensity, that means the threshold intensity for human ear. And you know, this has a fixed value. This is 10 to the power minus 12 watt per meter. Although for different detector, this threshold value will be different. But the sound level has been defined with reference to the threshold intensity for human ear. Okay. So I naught is fixed. This is 10 to the power minus 12 watt per meter square. And I is the intensity of sound whose sound level is to find. I is the intensity whose sound level is to find relative to this I naught. Okay. In fact, when you will express the intensity on this logarithmic scale defined by this equation A3, then actually this sound level is measured in a unit which is called decibel. Actually, logarithmic value will be always a number, but for convenience we use the uh, unit here. But when you will try to find that unit on the basis of this expression, then you can't find, because according to this expression sound level should be unitless. But when you will say that the sound level of this sound is 5, sound level of this sound is 2, it will not appear like a particular value of anything. So we use a practical unit for it, that is decibel. Okay, so sound level defined in this equation A3 is expressed in decibel. Now let us see what will be this sound level when we take the I is equal to I naught. I is equal to I naught. Then what will be the sound level? When I is equal to I naught, that is 10 to the power minus 12 watt per meter square, it means you are now going to find the sound level for the threshold of human ear. Then you can see sound level will be 10 log 1, but log 1 is equal to 0, so this will be 0 dB. So let us see how it is more convenient. If you will say a common people who is not a physicist, who is not a mathematician, that the human ear can give response to an intensity which will be at least 10 to the power minus 12 watt per meter square. अगर आप कहते हैं किसी सामान्य व्यक्ति को कि आपका कान कम से कम 10 टू द पावर माइनस 12 वाट पर मीटर स्क्वायर के इंटेंसिटी को रिस्पॉन्स देगा, वो कॉमन पीपुल इसको नहीं भी समझ सकता है, क्योंकि 10 टू द पावर माइनस 12 उसके समझने के बस के बाहर की बात होगी. बट व्हेन यू से दैट यू कैन रिस्पॉन्ड द साउंड वेव whose sound level is at least 0 dB, he will easily understand. 0 is understandable number. आप जब कहेंगे कि आप कम से कम 0 dB के साउंड को सुन सकते हैं तो बड़ी आसानी से समझ जाएगा, है ना. दिस इज द यूजफुलनेस ऑफ दिस स्केल. ओके, सो ह्यूमन ईयर कैन गिव रिस्पॉन्स टू द sound whose sound level is at least 0 dB. At least 0 dB. So this is the threshold value of sound level. 0 dB is the threshold value of sound level for human ear. Okay. Now let us see what will be the sound level for the upper limit or upper range of human ear. The upper range of human ear or the maximum value of intensity that is responded by the human ear, although that will be painful to the ear, that is 1 watt per meter square. So when I is equal to 1 watt per meter square, then what will be SL? This will be 10 log 1 by 10 to the power minus 12. So this will be 10 times log of 10 to the power 12, and this will be 10 into 12 times log 10. But log 10 to the base 10 is equal to 1. So this is 120 dB. So 120 dB is the maximum value of sound level that is responded by the human ear. So the sound level, the lower limit of sound level is 0 dB, okay, and the upper limit is 120 dB, and between these all the sound level will be responded by the human ear. But a human ear cannot respond a sound whose sound level is less than 0, that will be not responded, and also this will not respond all those sound whose sound level will be greater than 120 dB. Okay. Actually, this decibel is also used as a relative measure to compare different sounds with one another rather than with reference intensity. If you have, let us say, two sound sources of sound, and you have to compare that this sound produced by source 1 and sound produced by source 2, Let us say its intensity is I1 and its intensity is I2. I1 is greater than I2 or I2 is greater than I1, or how many times I1 is greater than I2. Such comparison can be made in terms of sound level very easily. In this case, you can see if we consider that the sound level for the sound wave of intensity I1 is denoted by the symbol SL1, then this will be equal to 10 log I1 divided by I0. And sound level for intensity I2, if it is denoted by SL2, then this will be given by 10 log I2 by I0. So SL1 minus SL2, this will be 10 log I1 by I0 minus 10 log I2 by I0 to the base 10. And here this 10 will be a common factor, and you know log A minus log B is log A by B. So this will be log I1 by I0 divided by I2 by I0. I0 will cancel out and your result will be 10 log I1 by I2 to the base 10. So you can see, if we know that I1 is 2 times of I2, I1 is 2 times of I2, then the difference of sound level will be what? You do not know how much I1 is greater than I2. You know how many times I1 is greater than I2. Relative value you know. So if I have an idea that I1 is 2 times of I2, then the difference of sound level will be 10 log 2, and log 2 is 0.3 on the base 10, and so this will be 10 times 0.3, that is 3 decibel. So in this way you can see that we can use this decibel as a relative measure to compare the different sounds with one another rather than with reference intensity. Okay. So in this way we have completed the concept of intensity in very brief, and I hope you have definitely understand each and every aspect of this lecture. Okay, thank you very much.